Hi, I'm Ryan Nickel, CTO at DSA Ocean, and today I want to talk about the process of making a comparison between two versions of the same ship with just some variation in the hull. In particular, we're going to focus on the bow shape. So why is this important? Well, in the really early concept stage of design, you might be looking at different things like bow form factor, and you want to get some way of indicating, like, based on what you know so far, which way is the design going. Maybe there's a way you can tease out which kind of design might be better. So we're going to start off with a design that is a variant on the Generic Yacht 50-meter hull concept that we have. So I made these variants in Orca 3D in the Hull Assistant. So just firing up Rhino, Rhino here. When we eventually want to get the hull out, we'll just need to change the setting for Orca 3D there. So I'll open the Hull Assistant here. Now I put these together in advance, and the general idea here is that they have the same kind of fundamental parameters as the 50-meter generic yacht. That is to say, the values that we chose for this, 50-meter length, 9-meter maximum beam, 2.4-meter draft, displacement's kind of like a roughly 560 tons, 550 tons. So those are the things we're trying to sort of keep in line. Oh yeah, metacentric height's about 0.9 meters, but we're not going to be looking at that here. So the point is, with Orca 3D, with the Hull Assistant, there's many different things you can play with in terms of adjusting the bow form factor, fullness, all these different variables, and I've done that already with and the main point I want to show is, like, okay, how can we make a systematic comparison between two variations using a ship motion prediction program? So we're going to use ProteusDS to do that, and then the ship motion toolset to do a large yacht comfort analysis to see if we can tease out any differences. So here's the conventional hull. So it's just sort of got a nice sort of rake here at the stern. Now, for the purposes of importing it into ProteusDS and the ShipMo 3D toolset, I'm going to set, well, maybe before we do, we'll just take a quick look at the hydrostatics. So you can see I've got, 554 tons here for the displacement. Again, this is something I would keep an eye on to make sure you're doing a fair comparison between hulls. Now I'm going to set the draft to 0, and I'm doing that because later we're going to adjust the draft level within ProteusDS, and it just makes it a little bit easier to do that. So we'll go create the port side here. We do half the hull, and then it's mirrored in for the purposes of doing hydrodynamics calculations later. That's why we're just dealing with half of it. And we don't do the NURB surface directly. We're going to go quad remesh in Rhino here. I just want something real quick and dirty, so 500 I think is fine. We'll click preview to see what that looks like. There we go. Sometimes I like to leave the mesh over top, just to kind of see, is it generally following that shape pretty well? Looks pretty good to me. So, and if we hide it, this is the mesh that we're going to get. It's kind of coarse, but that's fine for a real quick check. So click check delete input objects. This is going to get rid of the NURBS surface for you. So that's everything that we need. Now what I'm going to do for the conventional bow here is we're going to go save as. And I've got some empty folders here. I can call this conventional hull. And I think we're all good there. So now I'm gonna delete that, and then go back to the Orca 3D Assistant, go to my Hull Assistant, and we'll look at the other variation that we wanted to look at here. So the vertical bow. So we'll open the Assistant here, preview the hull. So now we have a totally, the rear half is basically the same, maybe with some ever so tiny variations. But the main idea here is, like, okay, well, now we have a nice vertical bow. I'm not trying to say that this is an incredible yacht design. It's really just about demonstrating the process. But in any case, I think you can see this is quite different. When we look at the hydrostatics for the same draft, we've got 554 tons. So, just trying to keep that roughly the same, and the main dimensions are also the same, which is good. Okay, so we'll set the draft to 0 as before. Again, we're going to be adjusting that draft and displacement value within the ship motion process in ProteusDS. So we'll go create port hull deck transom. We'll do the quad remesh thing as we did before. Again, we just kind of want to do a quick preview here. Everything's kind of looking like the mesh is lining up very nicely with the NURB surface. I don't see anything poking out or drastically looking different. And then, the mesh sort of looks fine. And we'll go OK. Now, this red, you might be wondering about this red here. I've set a custom backface color. So that just helps me make sure the normals are pointing the right way. There's a video, a separate video you can learn about and see what that's all about. But anyway, this is looking good. So we'll go save as and go to vertical bow folder. Vertical, call it vertical bow or vertical hull. Let's call it vertical hull. And go OK. All right. Now, let's look at our folders here. So these are totally empty. I'm gonna make some new projects. We'll open up Shipmo 3D, and we'll just go from scratch. I think in some ways this is easier. You could make a copy of an existing folder. Sometimes it's a little bit of a bit too confusing when you do it that way. So we're just gonna keep it simple today. So we'll, where's our vessel project? So we'll do the conventional bow one first. I do recommend you go through one project at a time because Shipmo 3D remembers the project settings that you had, and you can get confused if you go back and forth between projects. So just be careful about that. So one thing that's kind of nice is this file name prefix. It might be nice to add conventional bow or something like that, and then all the files have that. It just helps make it less confusing. Ship length between perpendiculars, well, that's 50. I'm not going to change too many different things here. 2.4 CG above baseline. So this is a little tricky. Obviously the metacentric height is a function of both the vertical CG and the hull shape. Generally speaking, we want to be iterating on this to make sure we have the same metacentric height, and it's pretty low for yachts to keep them sort of nice and comfortable around. And our Generic Yacht had a 0.9 meter, so that's what we're going to be aiming for. I'll show you how to make some adjustments on that. Early stage design, we're not going to be messing with stabilizers or rudders or propellers, so I'm just going to set all those to 0, and we'll leave this as read only. It should copy it amongst all the applications from here on in. So we'll add new data, panel hull, and we want to go down to hull geometry source, and we go to wavefront OBJ, and here's where we pick our conventional hull. So we'll save and run this. Okay, so first thing, let's take a quick peek at what it did, and we should see, I really like this ship parts thing here. So here we see the wet hull in yellow. That looks about right. Nothing weird poking out. It's not sideways or anything like that. Okay, so let's go back to panel hull. Now, I mentioned keeping an eye on the metacentric height. So if we go view output, and then you'll see it echoing back, displacement, things like that. I have noticed the displacement is a tidge smaller than the estimates from tools like Org3D or Delft. It's just a few percent smaller, but we're basically on the same ballpark of 550 tons there. Metacentric height, 0.910 from hydrostatics. So this is kind of making sure we have the same kind of roll restoring stiffness, at least onset stiffness. So I'm happy with that. I was playing with this beforehand. So if you needed to make an adjustment, you can make that here and just adjust the number up or down a little bit to get it closer to what you want it to be. But we're good with that for now. So we will go to add new data now to panel lid. And wet panel hull file name, you're just picking the wet panel hull file we just made in panel hull, so we're good. Most of the time I find the defaults work fine, so we'll run that. Didn't have any issues. We see pink on the interior area. That's going to give us some numerical quality. enhancements when we do the radiation and diffraction, so that's looking good and didn't have any issues. So we'll go add new data, rad diff, the wet panel hull file name. Again, this is what we just made in panel hull. So we'll click on that, wet panel hull lid. Yes, there's our lid that we just made in panel lid. Now I think generally these are a bit conservative for encounter frequencies. It's ShipMo3D is trying to guess what you need based on your length. That's fine. Now the diffraction param. Normally I would recommend you do radiation first, make sure everything's copacetic. I'm pretty sure this is going to be good though. So we'll go straight to doing a sort of, if you will, a speed run on diffraction parameters. Now a speed run, I'm just saying, is let's just do the conditions we need for doing an ISO large yacht comfort analysis, which means 0 and 12 knots. So we'll do, well, you can do it this way with a jump at 12 knots, and one direction only, bow quartering. That's 135 degrees. So not stern quartering, but bow quartering. The only thing to remember here is the ISO large yacht operability analysis, that large motion affected comfort analysis. It covers quite a range of wave frequencies, and I found 2.5. Just changing that maximum to 2.5 seems to work pretty well. All right. Well, yeah. Let's see what happens. I'm going to turn off parallel processing because I want to run two cases side by side. It's I don't want the system to get too bogged down with that, so we'll go save and run. Okay, so that's our conventional bow. Let's make a brand new project for running the rad diff for the vertical bow. So we'll go new project, and where's our vessel projects? So I'm just going to use this folder here, and I'm going to call this file name prefix vertical bow. We're doing something similar here. Ship length between perpendiculars, draft at midships 2.4. Let's set these guys to 0. Now height of CG, we might need to iterate on this one a little bit, but let's see. For vertical CG. Okay, so we'll save all that and go new data, panel hull, and we're going to go scroll down a little bit here, and we'll go hull geometry input option, wavefront OBJ, and we'll pick our OBJ file. Oh no! Now see we're in conventional hull. Make sure we're in the right working folder here, vertical hull. Okay, and run that. Let's see what we got out of this. So we'll go plot panel hull now, and kind of looking up ship parts, and yeah, things are looking pretty good there. The wet part in yellow is looking about right. You know, a little bit of a coarse mesh, but I think that's all right. Notice the mesh looks a little different along the waterline. That's normal. That's just automatically refining the mesh along the waterline to help with hydrodynamics calculations. Now let's take a look at the other parameters. So we'll go view output, displacement 547. Well, again, it's a little lower than Orca 3D. But this is the same as the other one. So, you know, again, want to make a fair comparison, make sure we're looking at the same thing here. And then the only difference is going to be the bow shape, more or less. Metacentric height, 0.992. Maybe that's a little high. So we'll go back here to panel hull, and maybe we'll make this just a smidge. What happens if we go to 3.2 and run that? View output. So now metacentric height from hydrostatics 0.892. Oh, that's real close to 0.9. So that's much better. I think that's good. We'll leave it there. So I've got 3.2 here. I'm going to go here back to the main project and then set this as read only. Read only. Okay, and then we'll save all. All right, now we'll go through the rest of the setup process. So add new data, panel lid. And you can see we got 3.2 showing up there. Wet hull panel file. Now this is just what we got out of our panel hull automatically. Don't expect any issues here. Sure enough, everything's fine. The default settings works great. We got some pink in the middle inside there. Great. Go to add new data, rad diff, and we'll pick our existing wet hull panel and then our lid that we just made for rad diff, and we'll leave the encounter frequencies here I'll change this to 12 and 12 just for the purposes of doing a large yacht comfort analysis. Now, if you wanted to look at this covers a wide range of sea states. It is just one relative heading, bow quartering. If you wanted to look at specific case-by-case comparisons, this is the time to add in a few, or use the range, or maybe use a few different speeds and things like that. But for now, I just want to do a large yacht motion affected comfort rating. Turn off parallel processing, and let's let it run. So we'll let these run for a little bit. For this kind of level of mesh, I expect this kind of calculation to take about 15 minutes or so, and we'll check on these in a bit and see how it goes. All right, you can see those two sets of radiation diffraction calculations have completed. Looks like it's taken both of them about 15-16 minutes or so. And taking a quick look at the radiation diffraction curves for monohulls, this is looking pretty good for both of them. And I think, as I mentioned, the defaults for encounter frequency might be a little bit conservative. You could probably do for reducing that a fair amount, but 15 minutes doesn't really take too long to calculate, and it doesn't hurt. Let's focus on here's the vertical bow. Let's do the conventional bow here. So to go through the process of doing a motion affected comfort rating, we need to finalize setting up the ship motion prediction model. Then we're going to generate a motion RAO, and then use that as an input into the ship motion toolbox to calculate the operability, or the motion affected comfort rating. So here we have the conventional bow project. As I mentioned, having that conventional bow name showing up in the file name prefix here makes things pretty clear. So we'll go to add new data. We want to go to build ship now. And we're going to pick our hull radiation and diffraction file name. Oh, see, this is remembering the previous one we were looking at. So we'll go to conventional bow here. This is just finished calculating here. And the dry panel file, that's optional, but something that you can get into if you want to look at some nonlinear time domain seakeeping analysis, which we're not going to do right now. Okay, this is one thing that's you gotta have some inputs for the radii of gyration. So if you don't have any information, there's lots of rules of thumb out there. I think the ITTC recommendations for roll radius of gyration is something like around 0.37, 0.35, 0.37, or even as high as 0.4 times the beam value. So that's going to be used 3.33. That's the same as our generic yacht project. And then for pitch and yaw, it's a quarter of the length. So we'll have 12.5 for those. Obviously, if you have better numbers, use those. But when you don't have a lot else, it's good to have a starting point. For doing the seakeeping analysis only, you don't have to do anything else except run. And again, you can do plot ship here. This would show, if we had any appendages, this is where it would show them, but everything, there shouldn't be any surprises here. This looks pretty good. Okay, so now to do the motion, to do the motion RAO, we do that in Seakeep regular referring to regular waves or sinusoidal waves. So we'll pick our ship for motion database file name. This is the output from build ship, so our completed model here. We got it pretty streamlined here, maybe just going back to build ship. Build ship is really great for, this is where you add all the bilge keels, any static foils, skags, rudders, stabilizer fins, anti-roll tanks, all that kind of stuff is where you're assembling all that. Might seem a little bit sort of, like, oh, what are we doing here? But certainly you're finalizing the ship motion model. So that's our first input here. Now, we do need to set the ship speeds. What I would do is, for our motion affected comfort rating, we need to do 0 and 12. So I just put in 12, skip by 12. We're just going to do 135 here for bow quartering. And here we do need to change the wave frequencies to include up to 2.5. That just makes sure we cover all of the wave frequency ranges that are going to be used in the motion affected comfort rating. So then we're going to do export ProteusDS response amplitude operators as well. So we'll save and run this, and that's all done. If you want to, you can plot, the motion RAOs and have a look at that. We're going to leave it at this sort of default resolution. This is pretty spiky. You might want to go back and maybe make this range increment a little bit more fine if you're not happy with how that looks. So we put 0.1. That might be good to just leave a little bit higher resolution there. You sort of capture more data around those roll RAO peaks and things like that. All right, so where did that file go? If we go back to our project folder here, now you see there's this new .dat file, conventional bow ProteusDS RAO regular .dat. We're going to use this as input into the ship motion toolbox file. So maybe what I'll do, just to make it a little easier for file navigation, I'm going to copy that in here. Helpfully, it's already added the conventional bow to the RAO name as well, so I know for sure which one that's for. Okay, let's minimize this for now. Let's go to the vertical bow project. So we'll go to existing data, add new data, build ship, pick our ship motion. Oh, we don't want conventional bow, we'll go to vertical bow. Here we are. Pick the vertical bow dry hull. Similarly, we'll use the same roll, radius of gyration. The rotational inertias we're assuming are going to be pretty much the same. You might have some insight here if you've got a really strange change in the hull form. You might want to account for that. But we'll just leave it like that for now, and we're not going to add anything else. And we'll likewise go to add new data, Seakeep regular, pick our ship model file, there you go, and put in 12, increment to 12, just do 135, make this a little bit higher resolution, so we do up to 2.5, and remember we changed this to be a little bit of a higher resolution increment for the motion RAO files. Oops, we forgot to check this box to export that, so we'll run that, plot the motion RAO. Okay, that's looking good. All right, so maybe before closing these, I'll just save these projects if I want to come back to it. Now, say you wanted to do an individual sea state comparison. That's where you use Seakeep random. This allows you to put in, pick a different sea state spectrum, John Swab, Brett Schneider, a significant wave height, peak period. The only thing with this is that you're just looking at one sea state at a time, and that's fine. Maybe that's all you want to do, but there's a big advantage using the ship motion toolbox and using the large yacht motion affected comfort rating. So you don't have to do this. I'm just, for organization, I'm just going to put them in here. Now let's load the ship motion toolbox, and we're going to do a motion affected comfort rating for both of these and see what the difference is. So first things first, we got to load the RAO. We'll start with the conventional bow. I'll write some notes here. 50 meter generic yacht conventional bow. Usually I like to do a 1.5 meter significant wave height. It gives a bit more insight into what's going on. Now, one thing about doing a large yacht motion affected comfort rating, you do need to locate the areas of concern. So this is the wheelhouse, dining area, a lot of the crew area, all that kind of stuff. One thing that's kind of nice about the default projects that we have is we've defined these areas for our generic yachts. So if you go to check out the sample projects, generic yacht 50 meter, you'll see generic yacht 50 meter areas. That's a text file. You know, I know that the hull form might shift things a little bit. We'll just make an assumption that they're pretty much going to be the same. And so you can select all those and hit Control-C to copy them. And then when you go paste all, it pastes all the areas in here for you to use. So that's kind of a nice shortcut. Obviously, you need to define these so they have meaning for your yacht design. But you know, we're sort of leveraging this to show the process and demonstrate things here. So okay, so we'll do the comfort analysis. And then when that's done, put this over to the side here. Now let's load the vertical bow. Vertical bow. So you can see I've now loaded in the toolbox the vertical bow. I changed the notes here to say vertical bow, and we'll run it, and we'll have something to compare against here. So what it's doing here is it's calculating the ship motion performance across a range of wave periods. So this is a peak period of, it's using 1.5 meter significant wave height for everything, and it's calculating ship motion in a 4-second peak period spectrum, 4.5, 5.5, and so on, all the way up to 10.5. So we're going through a whole range of calculations of ship motion performance. And then the ISO 22834 standard has 2 sets of criteria: the incidence of motion sickness and the effective gravity angle at every location, and that's what the star rating is here for. So you have you've got something to compare against in different areas. But I mean, to just jump to a final answer here, you can see we got 45% for the conventional bow, a little bit lower, 42%. So, you know, starting to get to be like, you know, a marked difference in performance just from the bow hull form factor. And that might kind of give you some insight into like, okay, well, maybe there's some advantages to doing this hull form versus the other. There wasn't anything particularly special I had done for the hulls that I generated. There might be a smarter way of kind of shifting, you know, adjusting the prismatic coefficient or whatever. Obviously, you want to keep the displacement kind of similar, but here there is, you know, you're starting to get a difference in results here, and it might give you some insight into like, well, you know, what bow form factor might give you some advantage in terms of motion affected comfort. And the nice thing about this toolbox and the ISO standard is you're doing a ton of calculations. So we got 0-speed calculations as well as the 12 knot results here as well. And you're starting to get some insight into like, okay, well, what's really going on here? It is limited to, even though it does cover a wide range of sea states and 0 and 12 knot speed, it is just looking at bow quartering. So you might get some more insights if you wanted to explore a case-by-case sea state analysis, but certainly you cover a lot of ground when you do things this way. All right, so the main goal was to show how you could go about doing a comparison to the same kind of ship with a different form factor in the hull, and I hope you got some insight from that. All right, thanks a lot for watching.